Okay, welcome to the next day in class. Today we're going to talk about mainly addition strategies, but we will also speak a little bit what you see here, the different sets of numbers that we have and the closure property. And some of this stuff may seem super easy, but just, take it, if you're really good at math, you might be like, wow, this is way below my level. But my hope is that if you are really good at math, you think, oh, I never thought of it that way before. Or if you struggle with math, you start to really grasp these concepts well. So maybe if you ever do teach it to someone, whether it be your students or your own children or a friend, you have a good firm grasp on basic number sense and your addition strategies. So here we start off with our different sets of numbers. Now when I first learned these, I thought they were a little ridiculous. Like in my Algebra 1 class, I thought, man, what does it matter to separate them into natural, whole, integers, and all this stuff? But as I learned more and more math, I began to appreciate it as you work in just the natural numbers or just the whole numbers, or if you're trying to understand, why are the irrational numbers, why aren't they a part of this group over here? So as you get into higher level math, especially like abstract algebra and those sorts of things, this becomes even more important, but it's also important that our younger math students understand the basics behind these. Another thing, like look at natural and whole numbers here. We'll go ahead and start talking about some of these. The natural numbers are like what you naturally start counting with. When I teach my children how to count, I don't start with 0 or negative. That seems a little confusing for them. I start off with, there's 3 apples there, 1, 2, 3, or 3 crayons. So they learn how to count using your natural numbers. It's your natural way of counting. Then you get to whole numbers, and it's the natural numbers, except for you also include 0 there. Now, when I first learned this in Algebra 1 in high school, I remembered like, hey, the whole has the O right there. And so for some reason that just helped stick in my head that you include the 0. It's like I just pretended like that was a 0 instead. So it's everything that's natural plus the 0. And that to me also seemed ridiculous in high school until later on I learned that there were civilizations that didn't even understand the concept of 0. Like, why would you include the number 0? Think like the Romans and how they used Roman numerals, and none of the Roman numerals have 0 in it. And we've got an article we're going to read this week on the special case with 0. The next set of numbers we go to are the integers. And the integers are the whole and natural plus the negative values of those natural numbers. So it goes dots here mean go to infinity forever there on both sides. But you've got negative numbers now, which were once again in certain civilizations, they never even looked at that as even a possibility. Like, what does that mean to be, to have a negative number? You can't count to -5, at least when you're counting objects. But if you're talking about debt or a deficit of some sort, then negatives make sense. So that took a while for civilizations to start to really accept that idea of what a negative meant. Then we have rational numbers. Now, rational numbers are when students start to maybe need a little more explanation on it. Rational numbers, the technical definition, if you look it up in a book, is any number that can be written as a over b, where a and b are integers and b does not equal 0. So you can't divide by 0. Remember, fractions like you're dividing there. So they always say whenever you got a fraction in math, that bottom can't equal 0, or you get an issue. So it includes these numbers over here, because if I want to write the number 4 as a fraction, you could write it as 4 over 1 or 16 over 4, 8 over 2. There's lots of different ways I can take these integers and write them in a fraction form where the bottom's not 0 and it is equal to 4. So 4 is also a rational number. But we also introduced this idea that it doesn't have to be like a whole number. It could be a fraction of a number, like 1/2. That doesn't fall in the whole natural integers, but it is a rational number. And we know the decimal equivalent of that is 0.5. So rational numbers is going to start including our decimals that can be written as a fraction. So 0.5, you might think, well, what about 0.3? You've seen decimals that go on forever like this. So 0.3 forever can be written like that, or you might see written as 0.3 with a bar over it to show it repeats forever. But remember, the fractional equivalent of 0.3 forever like that is 1/3. If you were to punch that in your calculator, 1 divided by 3, you would get this decimal equivalent. So even though this decimal is what we call non-terminating, means it doesn't end, 1/2 is terminating because it ends at 0.5, it doesn't keep going. Even though this is non-terminating, doesn't mean it's not a rational number. So a rational number is any number that can be written as a fraction. So all of the integers are rational, all of the whole numbers are rational, so are all the natural numbers. And then plus you have these numbers that are in here that don't fit into these three bubbles, but they are still part of the rational numbers. So everything that's natural is whole, everything that is whole is an integer, and everything that is an integer is a rational number. And then we've got these additional rational numbers in here that don't fit these three bubbles. Now, so you say, well, if that's rational, what does irrational mean? And irrational is where we get to numbers that cannot be written as a fraction. So, for instance, we have the most common ones I've written already right there, pi and the square root of 2. So if you look at pi, most of you, hopefully, if not, if you don't remember this, I'll show you, is 3.14. A lot of people have it memorized that far, and it keeps going, 159, and we know it goes on forever. You've probably heard of people that have memorized, so many digits of pi. It doesn't end. It just goes on forever, and the pattern does not, there's no pattern to repeat there or anything like that. So it's non-terminating, and it doesn't repeat its pattern in here. And we have it to where we can't come up with just two numbers and write one over the other. That's the equivalent of pi. You might get close. If you think like 21 over 7, what does that equal? That equals 3, right? 3 is close to pi, but it's not exactly pi. The Egyptians would use the number 22 over 7. And if you divide 22 over 7, you get a number that's even closer to pi than 3, but it's not quite pi. Even when we use in our calculator 3.14, that's not exactly pi. It's an approximation. It's really close, but you're cutting off some value here when you use 3.14 for pi. So since no number or no fraction can equal pi exactly, we say that pi is irrational. Same thing with square root of 2. There's no fraction that can equal the square root of 2 here, so it is also irrational. So this bubble and this one right here, they all fall under the real numbers. So you say, well, what's real, or what's the opposite of real? The opposite of real is imaginary. So if I was to zoom out of this and expand it further, we'd have the imaginary numbers somewhere off to the left. And imaginary numbers are when you get into things like square roots of negative numbers, like the square root of -1. So that is not real. Let's just move him outside that bubble. He'd be over here somewhere in the imaginary world. And then outside of all that, we have complex numbers. This is what we're mainly going to focus on here, because this is all on elementary and middle school math, and you typically don't get to imaginary and complex numbers in those. Now, today we're going to just mainly focus on the natural numbers and addition strategies for that. We might sometimes refer to these others, and as we move through this course, we'll get to the others, or at least touch on some of them. We won't do too much with the irrational numbers, but we'll see it when we talk about geometry, and then we'll see some additional things with whole numbers, integers, and we definitely want to talk about rational numbers, because so many people they have fears of adding, subtracting, multiplying, dividing fractions, so we want a better understanding and a firmer grip on rational numbers. But today's lesson is mainly going to focus on natural numbers and adding them. Tomorrow's will be subtracting them, and then finally we get to multiplying, dividing them before we expand in our number sets here. This file right here I've got it in our resources. If you want to download it, you can look it over. You can download it and print it and add to it if you want to. It's cut off here at the bottom of the screen, but it's a complete well, I guess ellipse here is the correct term. It's a complete ellipse. It just gets cut off on the video while I'm recording here. But yeah, so you can download that and have that copy for you if you want it. One of the first properties I want to talk to you about here is the closure property. And this property becomes more important as we get into abstract algebra later on in math. But I want to give you some examples. So I just took a small section of this larger Venn diagram here and just kind of zoom in a little bit on it. We're looking at the natural numbers, and we want to say, what does the closure property mean? You may not have seen this property in algebra because it's not discussed a whole lot in high school algebra. But it's a pretty easy one to grasp once you start getting it. So if we talk about natural numbers, and let's say I take two natural numbers and I add them, like 5 plus 12. When I add those two, I get 17. Take another two natural numbers, 3 plus 2. I get 5. Now in both these cases, I'm adding two natural numbers, and I get a natural number. Same thing here. I'm adding 3 and 2 natural numbers, and I'm getting a natural number. So in this case, and I can't think of any out there to where I would add two natural numbers and not get a natural number, we say that addition has closure on the natural numbers. Same thing with whole numbers. That's just adding 0 in here. I would still get a whole number anytime I added two whole numbers. So addition has closure on the whole numbers. Same thing with integers. If I added -3, which is an integer, plus 5, I would get 2. All three of those are integers. So it has closure on on the integers. Now, the same is not always true, we'll see, with subtraction. And we'll go through each time we talk about a different set and remind you what closure is as we do this, but I just want to give you an overview. So for instance, if I were to say 5 minus 2, I'm just talking about the natural numbers right now. If I said 5 minus 2, both of those are natural numbers. Positive 5, positive 2, and I'm subtracting. I get a positive 3, which is also natural. So far it looks like I've got closure on the natural numbers. But what if I were to switch this around and do 2 minus 5? What does 2 minus 5 equal? Well, it equals -3. So this right here is a natural number. This is a natural number. But this right here is an integer. A lot of times we use z for integers. I don't know why. I guess I gets confused with imaginary. So I got natural minus a natural equals an integer. I needed that to be a natural to say that there was closure in the natural numbers for subtraction. So here the closure property does not hold for subtraction and the natural numbers. Okay? So even though it works sometimes, it doesn't work every time. So we have no closure when we're talking about subtraction and the natural numbers. Now, whole numbers, same thing. No closure there. Notice we got, if we were to do 3 minus 8, I get -5. I got whole number, and then an integer. So we have no closure over the whole numbers. It only takes one, what we call a counterexample, to prove that the property does not work here. Now, if we could talk about integers, now we have closure over the integers, because notice I've got integer minus integer equals integer, integer minus integer equals integer, integer minus integer equals integer. So if I go to the integer set, then I can say subtraction has closure over the integers. Okay? So if you have questions on that, let me know, and I can give you some more examples, or we can talk it out a little bit further. So on each of these, if we can do mental math, then I think we can really demonstrate we know, have a firm grasp on number sense. And on all of these, any type of operation we're doing, we're going to start comparing different strategies. Now, most of these we have a traditional algorithm that we learned in school. So for instance, this first example here on the left, if I were adding this or using the traditional algorithm, I might say 6 plus 5 is 11, carry the 1. 1 plus 3 is 4, plus 2 is 6, and I get 61. And so that's one way to solve that problem, and there's really nothing wrong with that. However, sometimes, there might be an easier way. And what's easier to one person may not be so easy to another person. So some people, they can look right at this and they do it in their head, just like I did on paper. But you don't want to assume that all of your students learn the same way or that they see everything the same manner. And I don't want to do the same with you. I'd also like for you to know multiple ways to do things, because I think it's going to make you more, just stronger in your math, I guess you could say. And so I want to build up that basic number sense and see how you do things. So with this one, I want you to think, if you had to do this in your head, would you do it this traditional way? I mean, if you did, there's nothing wrong with that. I've got plenty of students I talk to in class when I'm teaching this class live that, they're like, that's the way I would do it. But usually I have some students that would do it a different way. So see if you can think of a different way you might do it. You can pause the video if you want. And we're going to look at some different ways here. So and when I do this in my head, I break this up into 30 plus 6 and 20 plus 5. So in my head, I look at it like that. And I add straight up and down here, and I say, okay, that's the same thing as 50 plus 11, which equals 61. So in my head, that's the easiest way to reach that point. Some other students that I've had before will do it a different way. They say, you know what, 25 is 5 away from 30. So they write it out in their head as this: 30 plus 36. And when they add those up, you get 66. But they say, wait a minute, I had to add 5 to this. So my answer is 5 too much. So then you subtract 5 and you get 61. And there are lots of other ways people come up with these mental math strategies. I would just like for you to have one or two that's your go-to strategy for doing it mental math, preferably not the traditional way, just to kind of, if you're always traditional with that method, just to kind of push you into trying something new. And if you don't really have a preferred way, I'd like for you to get down a way that's, nice and easy, and you can get better with your mental math here. Try another one here. Whoops, I accidentally hit forward there. Let's try this way right here. So try 53 plus 34. Try to do it a non-traditional way. So pause the video if you need to. This one's a little bit straightforward. In fact, I think the traditional method, when I first look at it, is probably the way I do this one. Because I see 3 plus 4, notice you don't have to carry anything. It's 7. And then 5 and 3 is 8, so you get 87. But you still might do it another way. You might say, well, I know 50 plus 30, and then you're going to add to that 3 plus 4. So you get 80 plus 7, which gives you 87. So we'll do some more for practice later on, some mental math there. But that's just, a good way. You do mental math, at least you probably encountered it quite a bit. And so to talk about the strategy, I think it's helpful. So now we're going to continue on to different addition strategies beyond the traditional algorithm. I showed you the traditional algorithm a second ago. So there's all sorts of ways we can demonstrate adding. And keep in mind, all of this, we're mainly sticking today to the natural numbers. So we're not including negative numbers or anything like that yet. We'll get to that next week. But for right now, I want to stay with just the natural numbers and different ways we can demonstrate our knowledge about adding them. So with our first one being the set model here, this is more of a physical objects that we're going to be putting together when we add them. So if you're in the classroom, I'd probably have you actually have some counter chips or some pennies or something like that and demonstrate this by adding those. With addition, it seems very oversimple, but remember, this is elementary and middle school math we're talking about here. So I start with the basics, but something like the set model will become more helpful when we start talking about adding fractions. So that becomes helpful there. So let's suppose we wanted to add the numbers just 3 plus 4, and we want to show that using the set model. Well, I want to get some objects out here, so let's see. Let me add those in, and I usually use the creative, let's see here, we got creative pen. We'll do smiley faces. So I've got 3 smiley faces here in this set, and then 4 over here in this set. And so as you're drawing these out, you don't have to use smiley faces, but whoops, not a circle. I was hoping to get the normal pen here. Pen. You've got one set here and you've got one set here, and we're adding those two together. So all I really want to see when you're doing your homework or a quiz and you're using a set model for just natural numbers like this is something that you see here. You've got 3 dots. You don't have to draw smiley faces, plus 4, and you get a total of 7 right in here. So you got 1, 2, 3, 4, 5, 6, 7. So there it is, the set model. Seems pretty basic, but remember, that's how we start off when we're learning how to add. You know, you add 3 crayons plus 4 crayons, you get 7 crayons. And by getting used to this, it will set us up later on so that we can do fractions a lot easier. Then we have the number line model. Now this number line model has negative numbers to it because it was pasted in here from the Smart software. But right now we're just going to talk about the natural numbers. So let's suppose we had 3 plus 4 right here. Now for number lines, when you're showing me how to add using a number line, what I want you to do is always start at 0, okay? And show me that we have a positive 3 first. So go from here to here, that's your plus 3. And then from 4 more away from that, now we're going to go 1, 2, 3, 4. We're going to jump 4 and land right there at 7. So we're taking a positive 3 plus 4. And if you do that, that helps us set up a little bit easier later on when we start talking about negative numbers and where we end up at. So that's what I want to see when we're using the number line model to demonstrate addition. Then we get into Cuisenaire rods. Cuisenaire rods are, I think, a great manipulative, especially when we start talking about fractions. Not only are they good for adding and subtracting fractions, I think they're really good for showing multiplication, and even better for showing what does division mean with fractions. Like, you know, what does it mean to say a third divided by 1/2? You know, how come, you know, why does that come out to be 2/3? That sort of thing. So we'll talk about that when we get into rational numbers, but for right now, I use this opportunity to kind of just introduce you, if you've never seen Cuisenaire rods before, to what they are. And so they were originally set up, I believe the man's name was Cuisenaire, that's why they're called that. But they're originally set up so that each of these rods are a different length, and each one has, or based off this original 1 centimeter by 1 centimeter by 1 centimeter cube, that we just usually give a value of 1. And so if you stack it up too high, it's the 2 value here, and then 3. So the 10th one right here could fit 10 of these white cubes into it. They're consistently colored the same way. If you look up Cuisenaire rods, the 1 value is always white, and the 10 value is always orange, and the colors are generally the same as you see in there. Now, what they don't have to be is they don't always have to be represented by these numbers here. Like, you don't always have to call the orange bar 10. It could represent 1/2 if you wanted to. But in general, when we're talking about natural numbers, this is pretty much how I'll leave it. When we get into rational numbers, we'll start defining what a whole is, and then the others can become fractions pretty easily. So there are some online resources. I'm going to show you one right now to where you don't actually have to buy a set of Cuisenaire rods to follow along in this class. You can just use the online version. But if you're going to teach it and you really like Cuisenaire rods and you become an elementary school teacher or middle school teacher and you just love them, then you can talk about, you know, maybe your administrator getting you a set to use in the classroom or several sets. They're not much. I think a set like this is maybe $10, which isn't bad if you're just one student and you just want to play around with them. But like I said, they're free online, the digital manipulatives. So I'm getting ready to show you that. Well, let's look at it right now. So here's our website that I'll try to share this with you later on in our resources. This is from the mathplayground.com, and here we have a grid, which we normally use some type of grid or graph paper when we're dealing with Cuisenaire rods. And if you drag this slider down here, you can pick which Cuisenaire rod you want to put on there. If you're not using these numbers, like I said, sometimes we don't use those numbers, you can click on this and it will remove the numbers, or you can keep the numbers on there. And then these other tools here you'll use later on. If you don't want the grid, you can take it off, or if you want to clear, like if you put a bunch of Cuisinart rods out there and you want to clear them, you can click on this X right here and it clears it out. So let's say we're wanting to do 3 plus 4 here. I can grab the 3 rod, and then I can grab the 4 rod, and as I put these together, I can see what the length is. And so you can say, does that equal 6? No, because the 6 isn't quite long enough, so it must be the 7, which we know 3 plus 4 is 7, but for somebody learning this, this is a great way to physically show them how a length of 3 plus a length of 4 equals a length of 7. It kind of starts to get that idea behind of measurement for lengths. If you've got a 3-foot board plus a 4-foot board, you can cover 7 feet with that. And so it's another way to show, without just counting objects, but to show the length of objects can be used for addition as well. And like I said, it's going to set us up so that we can start dealing with fractions. And these Cuisinart rods are closely related to the Singapore math article you're going to read this week, the rods they use in that. And it's a great way, because sometimes it's a great way to show basically in word problems, to give you something to manipulate, because sometimes word problems are great. You can say, all right, I've got, we go back to our apple example for lack of better examples off the top of my head. If you have 3 apples plus 4 apples, you get 7 apples. But sometimes word problems don't have that, manipulation you can use. If you got 20% off of, I don't know, a shirt that was on sale, how do you show that in manipulatives without getting out money or whatever? So the Cuisinart rods are a way that you can take pretty much any word problem, just about any word problem, and give something physical that the student can use to aid them in solving the problem. So there you are. There's that website. I'll share that link in our resources. And I guess I've done lots of advertising for Fruit Loops today as well. Let's see what else we have here in our addition strategies. So the next is another one that I like, and that is 10 frames. Now, I've got a lot of 10 frames already printed for you in the resources. So you can go there and print out those 10 frames if you want to use those as you do your homework or quizzes or whatever. But you can also use them in your own classroom if you like. I've put a few in here. You don't need to have 4. You could have more or fewer, just to show you a couple of different things with 10 frames here. Now, 10 frames are basically just what they sound like. It's a frame made up with 10 rectangles in there. And so if we're wanting to show something like 3 plus 4, you usually use some type of dot or chip in here, where I say, okay, here's to demonstrate 3. It looks like this. I've got 3 dots in there. And to demonstrate 4, I'm going to have 4 dots in the next one. Whoops, not a line. Let's make sure we have a dot there. And then we're going to add them together. So adding them together, you can say, okay, we've got 4 in the 1. And, for your purposes of showing me on your homework or whatever, like what 3 plus 4 is, this is what I want to see. I want to see 1 originally 3, 1 originally 4. And then somewhere in here you're saying, okay, we're adding these, and this right here becomes our answer, which is 7. Now, if I had a student in the classroom, like you can buy, I'll show you the link here, you can buy these so that they're magnetic and they can hang on your board if your board's magnetic. I might have a student come up to the board and show 3, then show 4, and then just move these 4 over into this one. And that's your basic sense there. We've got 3 plus 4, and that equals 7, but there's a whole lot more to 10 frames than just, you might say, what's the difference between this and a set model? I like it because it is grouped into tens. So what does this allow me to do? It allows me to see that 7 is 3 away from 10. And so I'm learning things like 7 plus 3 would be 10, or 10 minus 3 is 7, or 10 minus 7 is 3. You may not be saying that to the student, but the student starts to see what makes 10. You know, even right here, we see we're 7 away. You've got a row of 5 plus 2, that's 7. They can quickly see, or hopefully they quickly start to adjust and say 5 plus 2 is 7, so we're 7 away from 10 when we have 3. Same thing right here with 6. So they start to see those patterns and start to develop number sense when they use 10 frames. I use it a bunch when I'm showing my son different types of addition strategies. We frequently will pull out 10 frames. Let me show you the one we use. This is the 10 frames that we use. This is on Amazon. I don't make any money off of this. I'm not saying you got to use this one. It's just I like it a lot. It's magnetic. It's fairly large. You can put it up on the board. There it is next to a student. You can kind of see what's going on there. And so it comes with, I think, 4 of these frames and then a bunch of dots. You don't have to buy them like this. I just think they're great. And then I use the blue and green dots for other things. When you talk about counting methods, or we'll talk about later on the chip and charge model for addition and subtraction, or when I teach physics, I use it for positive and negative charges. So it's kind of hard, believe it or not, to find some circle vinyl magnets, and so I use that a lot in my own classroom. But obviously we use it for 10 frames as well. And even the cutouts, these, just another tip, these circles come in, they're actually all filled out into these 10 frames. You punch them out when you first get them, and you'll get some little, almost like when you peel stickers, like kid stickers, you get that frame around it's still on sticky paper. They're like little squares with circles cut out of them that are magnets. I save those and I glue them onto the back of other things that I laminate to make more magnets. So even the waste I reuse there, so that I can make even more manipulatives in my classroom. So $20, a little high for one manipulative, but you get a lot of different uses out of it. So not to mention 10 frames are, I think, great for teaching addition strategies. So you don't need to buy that for this class. Like I said, I try to keep this class as low cost as possible. There's lots of online tools you can use, and plus I'm sharing with you some resources where some of the 10 frames are already filled out. And so you can cut them out and slide them around. Some of them are just like this, where you put your own dots in. You could print out these and laminate them, and then just use an expo marker to fill them out if you wanted to, if you're helping somebody with their math. So you be creative. You're a teacher, or most of you are teachers out there, or future teachers, and be a little creative, and you can make 10 frames work for you. We'll show some of this maybe later on with subtraction as well, and how we can use 10 frames in other situations. The next thing we have here are base 10 blocks. We used base 10 blocks in the last lesson just to talk about place value, but we can also use them to talk about adding. So how do we show adding with base 10 blocks? So let me put up this problem here. I want to show you some with some regrouping, so it wasn't too simple, but at the same time requires a little bit of work, and I might regret putting this much out, but we'll see. Let's suppose we had 25 plus 88. So first thing I need to do is represent each number with these. So I got 25. Remember, our flats right here are going to be 100. So I don't want a 100 block, but I do have a 10 block right here. That's 10. This makes 20. And then I gotta have 5 here. So I've got 5 ones. And that's where I said I might regret doing this, because I could do a lot of this dragging over here. 4. And then 5. So that's 25. And then I'm going to add to that 88, which is going to require 8 of these rods and 8 of the single units. I'm going to pause the video and do that to keep you from having to be watching me drag all that. There we go. And so I've got 8 of these rods and 8 of these single units. That's 88. And so now I'm going to add these together. And when I add them together, I want to regroup if possible. So notice taking these 8 right here plus these 2, that's going to give me a total of 10 rods. Well, 10 rods is a flat. So I actually need to drag out a flat right here. That's what all the yellows add up to. Now, if I had 11 of these, say this was 98, I would have one yellow rod right here next to the green flat. And now when I add 8 of these red units plus 5 of these, let's do that. I have the advantage because I don't have to draw it. It's on the computer. I can just say copy and then paste it. Drag these over here. There's 8 and then 5 more. And so regrouping here, I got to say, do I have 10 of them? If I've got 10, then I can regroup it. So there's 8 plus 2 more is going to give me 10. So this group right here, I need to regroup that to get the answer right. So 10 of those cubes give me 1 rod. So they regroup to become that. And if you want, you can get rid of those. And I think I'm missing 2 right here. They get deleted too. That's a total of 10. And so I'm left with 3 right here left over. And so now I can say, okay, that's 100 plus 10 plus 3, which is 113. So if you're showing this to me and you're doing the base 10 blocks, what I want to see is I want to see the original written out, and then I want to see equals, and then show it to me regrouped, or you can, do a intermediate step in there where you put them together and then regrouped it. Most of the time students will draw it regrouped like this just because it's a lot of drawing to do. I know it's not as easy to draw it as I get to do with dragging things around. For this class, you could also do a digital manipulative if you can find a base 10 block digital manipulative like this and screenshot it and paste it into your homework if you want to do that. But that's your base 10 block addition strategy. The next we have expanded forms, which is kind of like what we did a second ago with mental math, 32 plus 59, say, where we could say this is the same thing as 30 plus 2, and this is 50 plus 9. And then, so we've expanded these into 30 plus 2 and 50 plus 9, and then we're going to add them up. So we end up with 80 plus 11, which is 91. So I will take that for expanded. It's kind of like what we do in our head when we do mental math. All right, and finally here in our addition strategies, I'm going to show you the lattice method. A lot of students do like this method, so it's a popular one, I think, for teachers to teach. Let's suppose we have 345 plus 276. And so I'm adding these two numbers. First thing we want to do is set up our lattice underneath, and I've kind of got it partially drawn here, but we still need to do these lines like this. And the nice thing about lattice addition is you don't have to start on the right side like you do with the traditional algorithm. You can really start anywhere. So if I want to start right here on the left, 3 plus 2 is 5. So 5 goes right there and a 0 right there. So 0, 5. 4 plus 7 is 11. 5 plus 6 is also 11. And so the last thing we got to do here is just add along the diagonal. So I get 1, 2, and 6, or 621. That's the sum of 345 and 276. So it's kind of cool. And we'll do lattice multiplication as well, which is also kind of a neat trick to that. Let's try another one. Let's do 5, 7, 6, 2, and we'll do 6, 9, 3, and then say 8, just to see what that comes out to be. So draw your diagonals, then add your numbers up. 5 plus 6 is 11, 7 and 9 is 16, 6 and 3 is 9, 2 and 8 is 10, and then we add along the diagonals. So we get 0, 10, and here we do carry the 1. 1 plus 9 is 10, so we got to carry that 1. We get a 7, 2, and then a 1. So this turns out to be 12,700 when we add these two numbers up. So that's your last one there. Once again, whenever I teach this or whenever I see other people teach it, there's always somebody that goes, "Oh, what's wrong with the way that it's supposed to be done the normal way?" And just remember that normal way is what we actually refer to as the traditional algorithm. And why is it traditional? I don't know. Is it better than others? Maybe, but maybe not to all students. And either way, I want you to start to see as we do things like even there are reasons why, this is good for mental math. This is good for number sense and understanding why do we carry those numbers over. We're actually regrouping. When we put 10 red blocks together, it's like carrying the 1. Students don't always understand right off the bat, what does it mean to carry the 1, or why do we carry that digit over? And yes, they might learn how to add, but do they ever have number sense to that? So I want you to learn these different strategies to demonstrate to me that you have the number sense, and also that you know how to do these strategies if you ever do teach someone else. This is great for showing, adding up to tens and subtracting as well, introduces subtraction. This is great for any type of word problem pretty much. The number line model gives you a good number sense of the order of numbers. And of course, this is your set model where you can actually start to see things get grouped together and why we add things. So there's reasons behind all of these too. And I just don't want to teach the traditional algorithm where there's no understanding and it's just you're like a robot learning how to add. There's a lot more richness to just basic addition than what's being always understood out there. So hopefully you learn some things here, and you can go back and refer to these videos. Make sure that you ask me questions if you have any questions on this, and we can work out more examples, or if you have questions on the homework, let me know so that way you're prepped well for the assessment coming up. Thanks for watching, and I hope you're having a great day.